Are you ready for a completely new topic? Yes, you heard me right. Completely new. Not groups. What? Chapter 12 is the beginning of ring theory. I said in the very first lecture that the main algebraic structures that we study in abstract algebra are groups, rings, and fields. We've spent how long on groups? 10 weeks or something like that? 25 class periods. Now we're about to do rings and fields. We got like 15 class periods left, 5 weeks or so. And yeah, that's less time for 2 more algebraic structures, rings and fields. And guess what? In talking about ring theory, we talk about rings and fields the very first day. Like today, right now, we're gonna, and fields. Because fields are rings. They're specialized rings, but they're special enough to have entire chapters devoted to them as well. Once we get to about chapter 19 or so, entire chapters are devoted to just fields, but I'll talk about them today. Now, I'm not going to give you a lecture, so to speak, like the video lectures that I give you here. What I'd like to do instead is approach this experimentally, you might say. Think about examples and make observations. We're trying to take concrete examples and abstract them to abstract properties. That's how math is done when it's first discovered and described and systematized, is people think about particular examples and then they notice commonalities between those examples and they abstract, right? They come up with the abstract theory based on the examples. Abstract theory doesn't spring from mathematicians' minds out of nothing, okay? Sometimes feels that way reading books, but it's not how it's done in practice. So what do we want to think about here? We want to think about examples. Then let's start with a fairly simple example. Our old friend Z, the integers. We already know that the integers form an abelian group under addition. We already know that. Z forms an abelian group under addition. And in fact, it's a cyclic group, an infinite cyclic group. Z is a cyclic group. Infinite. It's got 2 generators, 1 and -1. Right? The operation's addition, so we're not taking powers of 1. We're adding 1 to itself, or adding its inverse, its additive inverse, -1 to itself, an arbitrary number of times. Or you could also think about, corresponding to raising to the 0 power, giving you E. 0, 1 is 0. You do get the additive identity as well. That's just notation that in the multiplicative form corresponds to raising to the 0 power. In additive notation, you have to think of it as multiplying by 0, but it's not a literal multiplication. That's a group operation. It's just, n times an integer a means, or if n is a positive integer, and a positive integer means add a to itself n times. And a is a positive integer as well. But I'm thinking of a as being the thing that is being not exponentiated, but added to itself n times. Of course, since n and a are both positive integers here, I could also think of this as n added to itself a times. Okay, and you do get the same answer, as we know. We focus more on finite groups when we do group theory, not so much on infinite groups, but I will tell you that Z is the prototype infinite cyclic group. All infinite cyclic groups are isomorphic to Z. Okay, we never proved that. That might be worth proving maybe next time or something, but that is true. Okay, so we know this already. What's new in ring theory? Well, wait a minute. Why have we always ignored multiplication of integers? Well, so far it's because it doesn't form a group. But of course, we can multiply integers. And if you multiply two integers, it's still closed, right? It's still a binary operation. I multiply two numbers from the set, I'll get a number from the set. So its closure still works. Yeah, let's just start to write this out here. What about multiplication? Multiplication in Z. And when I say multiplication, I mean ordinary integer multiplication, as you've always learned. Closure still works. Put a check mark by closure. Multiplication of two integers is a binary operation. Associativity still works. Associativity, check mark. If A, B, and C are integers, and I'm multiplying them, I can multiply B and C first, and then multiply A by A, or I can multiply A and B first, and then multiply by C. In fact, commutativity also works, although that was not part of the definition of a group, right? We have abelian groups and non-abelian groups. Abelian groups means the operation is commutative. Non-abelian means it's not commutative. But we do have a commutativity of multiplication in Z. I am assuming A, B, and C here are all integers. We have a multiplicative identity. Right? The number 1 is a multiplicative identity. 1 times A equals A times 1 equals A. Yeah, this is for all A, B, C in Z. What about inverses? Anybody ever watch, what's the name of the show? Family Feud? You like Family Feud? Yeah, right. Family Feud's actually a very, very old game show. I mean, it was an older host in the past. It goes back to the 60s, 70s, I think. So does like Price is Right, the very old game shows. Only 1 and -1 have multiplicative inverses. No other integers do in the integers, right? 4 doesn't have a multiplicative inverse in the integers. It does in the rationals, 1/4. But 1/4 is not an integer. Only 1 and -1 have multiplicative inverses. Multiplicative inverses. I cannot spell today. Sorry that my writing's so small sometimes. Inverses in Z themselves, right? Multiplicative inverse of 1 is itself. Multiplicative inverse of -1 is itself. Yes, 1 to the -1 power is 1, and -1 to the -1 power is also -1. Why am I putting? Okay, I'm making my ones a little extra fancy sometimes for some reason. Don't always do that. Sometimes yes, and sometimes not. Okay. Nothing else has a multiplicative inverse in Z. Maybe even worse. Maybe even worse. is that 0 times any integer is 0. Maybe even quote unquote worse. 0 times any integer is 0. Is that a problem? Certainly true. It happens to mean that even when we consider the rationals, 0 still does not have a multiplicative inverse, even though all the other rationals do. That's what I'm getting at. We'll come back to that observation. So Z is a group under addition, but because inverses are a problem, it's not a group under multiplication. And even if you take out 0, it's still not a group under multiplication. Though if we, okay, here I'm already coming back to the observation. If you take 0 out of the rationals, we've talked about this briefly, Q star, the rationals take away 0, is a group under multiplication. R star, the reals take away 0, is a group under multiplication. C star, the complex numbers take away 0, is a group under multiplication. 0 is kind of problematic no matter where you are. Sometimes you want to take it away if you want multiplication to be a group. Well, you know, maybe it's not such a big deal that inverses don't exist and that 0 is there, this problematic element. Maybe we should just give it a new name. Call it a ring. But what is a ring? Is a ring just the multiplication part? No, rings are addition and multiplication. We've got 2 binary operations. Z is going to be a ring. In fact, we're going to say it's a commutative ring. We're not going to say abelian ring. We reserve the word abelian for groups. It's not that you couldn't say it's an abelian ring, it's just nobody does. If you did, probably somebody, an algebraist, group theorist, ring theorist, whatever, would know what you meant, but they use the word commutative. Commutative ring, meaning the multiplication is commutative. In rings, we're always going to assume the addition is commutative. Rings will always form an abelian group under addition. That'll be part of our assumption because it happens in all the important examples. That's why. Sometimes commutativity of multiplication will be satisfied and sometimes not. It's got an identity. In ring theory, we call the identity a unity. We call the multiplicative identity a unity. 0 is still the additive identity. And yes, you could say 1 is a multiplicative identity, but for emphasis, maybe for historical reasons, we call it a unity. A little strange, but we're used to strange by now, right? Unity. Okay, one example is not enough for a theory. What are other examples? Well, how about one of our, let's keep it simple. How about Z2? As a set, it's just 0 and 1. We know it's an abelian group under addition, mod 2. What's its Cayley table? Very simple. We're adding mod 2. There it is. Addition mod 2. Can we multiply? Right, rings are about 2 operations, addition and multiplication, I guess. Can we multiply? Sure, we can multiply mod 2. Multiplication mod 2. What is the, should I call it a Cayley table? Sorry, these are so far apart here. Maybe I shouldn't call it a Cayley table because 0 is still going to be problematic. That's not a group table, right? in the main matrix of the table, 0 is occurring more than once in this row and this column. That's problematic with groups. So no, I don't want to call this a Cayley table, but I could, I guess, call it a multiplication table. Reserve Cayley table for groups. Yeah, 0 is problematic. I guess if we took out 0 and just had the one element 1, that would be a one element group with very simple Cayley table. It's still multiplication mod 2. That'd be a trivial group. Very simple Cayley table. A one element group. Under addition, you'd call it a 0. Yeah, that would be isomorphic to Z1 under addition. A one element group just contains 0 under addition mod 1. 0 plus 0 is 0 no matter what. Is this, I mean, it's closed. Is it commutative? Yeah, it's commutative. Is it associative? Yes. You could verify all the possibilities. Yes, it is associative. Does it have a multiplicative identity? Yeah, 1. 1 is the unity. 1 times 1 is 1. 1 times 0 is 0. 1 times anything in the ring is itself. So this is also a commutative ring with unity. We'll come back to finite examples. Are there commutative rings without unity? Without a multiplicative identity? There are. Simplest example is 2z. What do you think I mean by that? Yeah, we've used this notation before. All the even numbers, all the even integers, I should say. That is a group under addition, a cyclic group under addition, isomorphic to Z itself. Isn't that weird? A proper subgroup of Z is isomorphic to the entire group. Weird, but true. The generators are 2 and -2. This is as a group under addition. It's isomorphic to Z. What's an example of an isomorphism? This is just a side comment, but a worthwhile side comment. An isomorphism from 2Z to Z would be to take each element of 2Z, call it M, and divide it by 2. Wait a minute, can division be operation preserving? M is an even integer here. So I can divide it by 2 and get an integer. Would that be operation preserving? Oh, it's I'm fooling myself there. I was like, that doesn't work. It's under addition, right? Yes, it's operation preserving. The operation's addition. And this mapping is 1-to-1 and onto. It's an isomorphism. 2Z is isomorphic to Z. 3Z is isomorphic to Z. 4Z is isomorphic to Z. 5Z's. There's infinitely many proper subgroups of Z that are isomorphic to itself. Blow your mind? A million Z. Billion, a Google Z. Doesn't matter. Not 0Z, because that would just be 0. But any other integer Z, based on what I mean by this notation, would be a proper subgroup of Z that is still isomorphic to Z. Weird things like that can happen with infinite groups. Well, we're doing ring theory. What about as a ring? Can we multiply even integers and get an even integer? Yes. Closure. Associativity still works because these are still integers. Commutativity still works. Multiplying integers is still commutative, but there's no multiplicative identity. There's no unity. One's not in there. Does anything else act like a one? No. Under multiplication. No. That's a commutative ring without unity. Coming back to finite examples. Let's up the game here a little bit. Let's go to Z3. Certainly it's a group under addition mod 3. We already know that. It's a cyclic group, in fact. So addition mod 3. Cayley table. It is a group. 0 is the identity. It's an abelian group. There it is. Cyclic group. 2 generators, 1 and 2. Again, as a group. I keep writing as a group when I'm using the cyclic generator notation. Because in ring theory, we're going to use this notation again, but with a different meaning. Not now, not today. Yeah, next week sometime. Next Wednesday or Friday, probably. We'll use this notation in ring theory, but it'll mean something different. What about under multiplication mod 3, which would be the most natural operation to try? Zero is still problematic. 0 times anything is still 0. This is not a Cayley table. It's not a group under multiplication. But I can still multiply these elements and mod by 3. 1 times 1 mod 3 is 1. 1 times 2 mod 3 is 2. 2 times 1 mod 3 is 2. 2 times 2 mod 3 is 1. If I did just focus on the 1 and the 2, get rid of 0, and consider this subtable under multiplication mod 3, that would be a group under multiplication mod 3. Group isomorphic to Z2, 1 would be the identity. It would be an abelian group under multiplication mod 3, isomorphic to Z2. Operations are different. Z3 take away 0 is just the set 1 and 2. It's a group under multiplication mod 3. Isomorphic to Z2, which in group theory means 0 and 1 under addition mod 2. Okay, so these are not groups under multiplication, but Z2 and Z3 are groups under multiplication when you take away 0. Could I call them Z2 star and Z3 star? Yeah, you could. We don't usually, but you could. What about Z4? As a set, it's 0, 1, 2, and 3. We already know it's a cyclic group under addition mod 4. Let's quickly fill in the Cayley table. It's a cyclic group. As a group, 1 and 3 are going to be generators, not 2. As a group. Okay, quickly fill it in. 0 is the additive identity. It is abelian. I can quickly fill this in. I'm adding mod 4. So that's going to do this. Quickly filled in Cayley table, right? Double check it. 2 plus 2 Mod 4 is 0, for example. 2 plus 3 is 5. Mod 4 is 1. What about multiplication mod 4? All right. See what happens here. 0 is still problematic, but it does help you fill in the table quickly. 1 is still a multiplicative identity. 2 times 2 is 4. Mod 4 is 0. That's problematic for Z4 star being a group under multiplication, right? It would not be closed. 2 times 3 is 6. Mod 4 is 2. 3 times 3 is 9. Mod 4 is 1. We focus on the non-zero elements in this part of the multiplication table. That 0 there is a problem. The set 1, 2, 3 under multiplication mod 4 is not closed under multiplication mod 4. It's not a binary operation of that set. Multiplication mod 4 is not a binary operation on the set 1, 2, 3. So the non-zero elements of this ring, this is going to be a ring still. The non-zero elements don't form a group. Well, they don't form a group for Z either. They did for Z2 and for Z3, but not for Z and not for Z4. These are all rings, but the collection of their non-zero elements under multiplication are sometimes grouped and sometimes not. That's the distinction between what makes a ring a field or not. A ring is going to be a field with two conditions. If it's commutative under multiplication, so it's a commutative ring. And if the collection of non-zero elements forms a group under multiplication. So you can say that as the collection of non-zero elements forms an abelian group under multiplication. That's what a field is. I haven't officially defined ring, at least not written it down, but I'm going to define a field. A field F. We're going to reserve typically in the abstract the letter R for a ring and the letter F for field. But again, fields are rings. A field F is a commutative ring so the definition of a field includes the word ring with unity. It's got to have a unity if every non-zero element is going to have an inverse. Okay, it's a commutative ring, so the non-zero elements are already abelian, you might say. I'll just say in which every non-zero element has a multiplicative inverse. Now, in writing this in the way that I'm doing, I'm also assuming that F has a 0. Because I said every non-zero element. Why can I assume that? Well, the reason is because 0 is always the label for the additive identity of any ring. Note 0 always exists in a ring by definition. Is the quote unquote the symbol or the label. I'll call it the symbol. for the additive identity in a ring. So I haven't officially even defined ring yet, but here I am defining field in terms of ring. I've hinted at the definition of a ring. Actually, there's one thing I didn't mention yet in the definition of a ring, and that's the distributive property. We've never mentioned the distributive property in this class before, have we? Distributive property. We haven't mentioned it. Well, first of all, because it's only relevant once you get to rings. And secondly, so far today, I've just focused on other things. Distributive property is a property that relates addition and multiplication. It's this. And if your ring is not necessarily commutative, you also probably want to write it the other way around. You want both of these things to be true. They'd be equal if the ring is commutative. And again, when I say commutative, I mean commutative under multiplication. It's assumed that the ring is commutative under addition. It's assumed that it forms an abelian group under addition. You want both of these things to be true, even if the ring is not commutative. These are distributive properties. I do want to show you one more example, or a couple more examples of rings, but let me just highlight something else here. Is this related to vector spaces? Yes and no. I mean, vector spaces and rings and fields are all abstract objects. They're algebraic structures. What went on in vector spaces? I've already emphasized that vector spaces always form groups under addition of vectors. In fact, abelian groups, and the zero vector is the additive identity. But I said so far with vector spaces, ignore scalar multiplication. Just don't think about it. Just think about adding vectors. If we put scalar multiplication back into play here, would that mean vector spaces are rings? No. We're not, when we do scalar multiplication, we're not multiplying two vectors to get another vector. We're multiplying a scalar times a vector to get another vector. That's different. It's not a binary operation in the sense we've defined it, at least. Two V, where V is a vector and 2 is a number, is a vector, and I'm multiplying them, so to speak, but it's not the multiplication of two elements from the vector space. It's an element of the vector space times a number. So it's not the same thing. You might argue, well, I learned we could multiply vectors like with dot products and cross products, right? Yeah, you can do dot products and cross products, but it doesn't make vectors a ring. It's not the same thing. Cross product comes closest, but it doesn't. I think it just still doesn't work. Cross products are only for three-dimensional vectors as well. Cross product comes closer than dot product. Dot product to two vectors is not even another vector, right? It's a number. Cross product of two three-dimensional vectors is a vector. That comes closest to making a ring, but I think there's still a problem. I'll have to think about that. Come back with it next time. It's certainly not a commutative ring if it was a ring, because you might remember D cross W does not equal W cross V. In fact, it equals the opposite of W cross V. It's anti-commutative. Yeah, I think, yeah, it is problematic in being a ring. Our property fails. I haven't thought about this example before, so I just thought of it there now. I think associativity fails, maybe. I'll have to think about it. I'll come back. Because we should spend our last little bit of time on a couple more important examples. If you write something like this, M2 Z, for example, as a set, this represents the set of all 2x2 matrices with entries from Z. Be careful here, though. We did talk about matrix groups of matrices. The most common example we talked about both in class briefly and in the lectures was GL to Z, for example, or R. Use a different color. Let's use R. I could have used an R here as well. I could let A, B, C, and D be real numbers. But this was the set of all 2x2 matrices with non-zero determinant. And we said that that was a group under multiplication. This is a different set. For one thing, I'm using Z instead of R. I could use R. I'm also not saying the determinant has to be non-zero. It does not form a group under multiplication, even if it was an R instead of a Z, because I'm not saying the determinant has to be non-zero. But it is still a ring, because it still forms a group under addition of matrices. An abelian group under matrix addition. And you still can multiply matrices in here, and the ring properties are still satisfied. In fact, it's a ring with unity, and the unity is the identity matrix. That's the quote unquote one, so to speak. It's a group under addition, an abelian group under addition, and still satisfies the ring properties. One more quick example, and then we'll end class quickly looking at the definition in the book of a ring. There's lots of examples of the following type, but this one's maybe a little bit more interesting than the average one. Z2 square bracket X. This is standard notation for, as a set, the collection of all polynomials with coefficients from Z2. In other words, all the coefficients are either 0 or 1s. Do know we're also saying these are polynomials, so they're not infinite series. So this means that at most finitely many coefficients can be non-zero, 1. This is a ring. In fact, a commutative ring. Under ordinary polynomial addition and multiplication, except you got to mod the coefficients by 2. I'll call that under polynomial addition and multiplication mod 2. When I say ordinary, I mean you do it the way you think you should do it. But you mod the coefficients by 2. So for example, x squared plus x plus 1 plus x squared plus 1. Add those polynomials in the ordinary way, get 2x squared plus x plus 2, but then mod the coefficients by 2, and it simplifies to x mod 2. The 2's go away. They become zeros. I can also multiply them. Oh, let's see. I'll multiply x squared times each term on the left, and I'll get x to the 4th plus x cubed plus x squared. Then multiply 1 times every term, and I'll get plus x squared plus x plus 1. Combine like terms. There's only one term to combine. It's the one with the x squared. 2 becomes 0. This simplifies to x to the 4th plus x cubed plus x plus 1 mod 2. The coefficients are modded by 2, not the exponents. That's a couple example calculations in this ring. And it is a ring under this operation. And it's a very interesting ring in a lot of ways. And we're going to study it a lot. Let's spend just 1 minute looking at the official definition of a ring in the book. A ring R is a set with 2 binary operations, traditionally denoted by addition and multiplication. There could be other kinds of operations that maybe make something a ring, but if there are, we're not saying what they are. We're talking abstract here. We use addition and multiplication in the abstract. It's commutative under addition. It is going to be an abelian group under addition. Associative property works. Binary operation, again, implicitly means closures, satisfied. There's an additive identity, the 0. There's additive inverses labeled negative A, not A inverse. Multiplication is associative and distributive property holds. Doesn't have to be commutative under multiplication, doesn't have to have a unity. If it is commutative under multiplication, we call it a commutative ring. If it has a unity, we call it the unity, the multiplicative inverse. One other quick bit of notation or terminology. When an element does have a multiplicative inverse, we call it a unit. Unity means the multiplicative inverse itself, the 1. Unit means it's an element that has a multiplicative inverse. Easy to get those terms confused. All right, have a good day.